Now, the first law of thermodynamics was stated in terms of cycles first, and then it was shown that the cyclic integral of heat is equal to the cyclic integral of work. Now, when the first law was applied for thermodynamic processes, the existence of a property, the internal energy, was found. Similarly, the second law was also first stated in terms of cycles which are executed by a system. Now, when applied to processes, the second law also leads to the definition of a new property, and that new property is known as entropy. So, the first law is said to be the law of internal energy, then the second law may be stated to be the law of entropy. So, in fact, the study of thermodynamics is basically the study of three E's, namely energy, equilibrium, and entropy. Now, in this series of videos, we'll understand what entropy is and how does it have some significance in the second law of thermodynamics. Now, the first topic of this series of videos is about proving that two reversible adiabatic paths cannot intersect each other. Now, this is a very easy concept that you must understand. Okay, and it violates the Kelvin-Planck statement. So, when you are reading this chapter from any book, you just need to understand that two reversible adiabatics do not intersect, because this kind of a situation will always violate the Kelvin-Planck statement of second law. Okay, and to understand it further, let's have a look at this diagram, which is a plot of PV chart. Now, in this we have one reversible isotherm and two reversible adiabatics. Okay, let a reversible isotherm, that is AB, you have two points on this, that is AB. Okay, it is drawn in such a way that it intersects the reversible adiabatics at A and at point B. Now, we have now three reversible processes. The three reversible processes are, you have one process as AB, the other process as BC, and the third process as CA. So, if you look at this, you have AB, BC, CA. So, this is actually representing a cycle, isn't it? Now, if you look at the diagram a bit more closely, this reversible isotherm, that is representing a constant temperature T1. Now, because it's a cycle, the area included, that is this area, it represents the work output in this cycle. Alright, but this kind of a cycle is not possible at all. It is an impossible cycle, since the net work is being produced in a cycle by a heat engine that is exchanging heat with only a single reservoir, and it is represented by the process AB, which is on the reversible isotherm at temperature T1. You need to have one more isotherm to complete this cycle, or to make this cycle a valid cycle or a possible cycle. Okay, so because this kind of a cycle is not possible at all, therefore the assumption of the intersection of these two reversible adiabatics at point C, it is wrong, it is incorrect. Okay, so through one point there can pass only one reversible adiabatic. So this is a very easy explanation of why two reversible adiabatic paths cannot intersect each other. Now, after this very short and important concept, let's move on to the next video of this topic and talk about the Clausius theorem.